So in the different kind of materials called shape memory alloys. So the basic property of these alloys are they are able to remember so-called their original shape and return back to it using the principles of phase transformation. So as we know that martensite forms upon rapid cooling, and we have also seen that martensite does not reversibly transform back to austenite under any circumstances. But there are certain set of materials called thermoelastic, also having a martensite, also called thermoelastic martensite, which can reversibly transform to austenite and back to martensite upon heating and cooling. So not only this, so if heating and cooling is replaced by application of stress, they show similar behavior as the temperature changes. So we see that some of these materials like iron and 30 nickel and gold cadmium alloy show this particular kind of behavior. So we can see that in iron at 30 nickel alloy, the austenite martensitic transformation temperature is close to 100 degrees, whereas the reverse transformation back to austenite is greater than 400 degrees. So there is approximately 400 degree hysteresis which is seen in this material and which if wanted to be exploited in applications is not very attractive from the real practical point of view. But another alloy which is gold cadmium, we see there is very small hysteresis, that is only 15 degrees Celsius between the transformation of martensite and austenite. So this alloy becomes very attractive from the point of view of exploitation in the shape memory alloys. And apart from this, some of the other advantages of this transformation are there are very small shear strains involved in the transformation, martensitic transformation in these alloys, and which are accommodated mostly under elastic deformation. So there is no plastic deformation, and they are very used in as a smart materials in the sensing and other applications. So there is another very famous shape memory alloy, that is nitinol, that is equal atomic proportion of nickel and titanium. So how does it show, what is the benefit it shows? We see at the stress strain curve of this particular alloy as a reference with the stainless steel, we see that stainless steel is almost there is no elastic, very less elastic strain in the region which is being considered up to stress of 600 ampere. Whereas in the nitinol alloy we can see there is approximately 8% elastic strain, and in the loading direction, that is if in the stress, when the stress is being applied, and during unloading, when stress is relieved, we are able to recover the strain. So this is a very typical stress strain curve which is not usually seen in the ductile materials behavior, and this is carried out at 10 degrees Celsius, and we can see there is a small hysteresis which is visible during the unloading and loading curves. So to give an example how this alloy can be used for a real application, we see that let's consider a rod of NiTi, and let this rod let us bend this rod in the L shape on the application of stress above the martensitic transformation temperature. We don't want the martensite to form using the cooling technique, but instead of that we are applying stress and we are forming but as we know that our application of 500 ampere, the material NiTi will transform to martensite. It will show a large amount of elongation, so we are able to transform into a L shape bend rod, and the martensite forms in the material. So, and if we release the stress again, as per the diagram, stress strain diagram, it will reverse back to the original shape, and it will have the no stress, or the martensite will transform to austenite. Now if instead of reverting back the stress, we quench the rod in the L shape as it is below the martensite temperature, even after that, even if we release the stress, the martensite will not transform austenite, because we have given it a thermal activation, and it is now having a thermal driving force to transform to martensite. Now this material, if left like this, and if it is heated again, without application of any stress, it will transform back to austenite, and it will recover its original shape. So it is, you can see, not only phase transformation, the shape is also being recovered in this particular transformation. So that is why these alloys are very attractive in the sensing or actuator application, and they are named as shape memory alloys. They are able to remember the original shape in which they were present.